Good evening, good evening, good evening everyone. It is 9 o'clock, it is Wednesday evening, and it is that time again. It is time for some physics. This evening we are taking a look at speed, distance and time graphs. The bane of everyone's existence on the start of the double and triple award exams, graph question time. The actual physics behind this, relatively straightforward actually. It becomes graphical and a lot of it looks very much the same in certain contexts. So let's start with the basics. Okay, so our first position is that imagine I start here and I travel to a certain other point over here. Okay, the physical space between this point and this point is known as the distance travelled. Okay, nice and easy. Okay, and if I time that, I get a time for getting from point A over here to point B over here. Right, now I can make my way from point A in whatever way I choose to do so. I can run, I can hop, I can take a rocket, I can shuffle along on my butt, whatever. In fact, I can change the way I get from one place to another as I go along here. It doesn't really matter. But what I do want to do is I want to be able to calculate how quickly I've got from A to B. Now, to do this, we use the equation that you've almost certainly come across before. That is speed, not sped. Speed is equal to distance travelled divided by time taken. So that's distance travelled divided by time taken. You've almost certainly seen this somewhere in either maths or in earlier science. Okay, it's one of the kind of basic equations. It's unfortunately, while it's not wrong, not quite 100% right, because it's misleading. That this word here, speed, implies that you're telling me something very, very, very accurate. But if I take 1 hour to get from point A to point B, I could have done so by walking at a nice steady pace from A to B. I could have done so by jogging a bit, walking a bit, having a sit down, then walking on a bit further. I could have just stood at the start for like 59 minutes and then shot myself out of a cannon to point B. There's all sorts of things I could do. So what I'm actually doing here is not measuring my speed in the slightest, but what I'm doing is I'm giving you some form of idea of the average speed. Okay, like on average, over this course of time to travel this distance, what was I doing? Okay, so moving on then. What we need to then be able to do is take some units and take some measurements of this. So just like in our equations video cast last time, distance travelled is going to be measured in meters. Time taken is going to be measured in seconds. So therefore my unit for average speed is going to be the meter per second. Now that can change. For very, very long distances travelled, I can use kilometres and I can use time taken in hours, okay, to give me kilometres per hour. Or for Team Brexit, if you're out there, rather than using kilometres like those dirty Europeans do, we can use miles like our intelligent friends in the States do. And again, that's per hour. It's because even the Americans use the same time as us, and we can get miles per hour. Okay, so our average speed will be measured in whatever the unit for our distance is divided by whatever the unit for our time is. Straightforward. Okay, now the real fun comes from when we're not actually going from A to B. That's of limited interest to us. What we really want to look at is what happens if I go from point A to point B, then on to point C, and then maybe on to point D after that. That's a little bit more interesting. Now, in this case, I go a distance, and a distance, and I can add this all up and find out how far I've gone. So this is point C, and this is point D here. And I might get some more information. I might get some information about what I'm doing along here. And then at that point, it stops being a single calculation. It starts being multiple calculations, one after the other after the other. What was my average speed from A to B? What was my average speed from B to C? What was it from C to D? And then I start getting some real problems because there's so many numbers coming at me that I stop receiving any form of real idea as to what's going on. This is where graphs become useful to describe things. Instead of describing my distance travelled from A to B and then B to C, I'm going to stick it all on a graph and just label these points. All right, so the graph we're going to draw is like this. We're going to do a y-axis up here of distance, and then the appropriate unit, let's call it meters for the sake of it, and an x-axis across here of time, and again we'll put it in maybe seconds. Now immediately you should be having a problem with this, because everything you know about independent variables suggests actually that the distance is what you're in control of. Like, you control where you're going from and where you're going to. And I agree. Under normal circumstances we would put distance across the bottom as our independent variable. But we're doing this for a very specific reason. What we want to do here is we want to engineer the gradient of this graph to mean something. And again, for those of you who have been with us and been doing the rearranging equations and graphs things, you should know that the gradient is equal to the change in y divided by the change in x, or the rise over the run, to use like a slightly more common and low level expression for it. So the rise over the run. Now in this case then, the rise in this graph will be my change in distance. My change in distance. And just stretch out a little bit. And my run is the time taken for that change. Okay, so my gradient is change in distance divided by time taken. So the gradient of my graph is actually the average speed. And that's what makes this useful, because we can visually inspect the graph and get an idea of what our average speed is. Okay, so the gradient is the average speed. That's what we want. Okay, bigger gradient, bigger slope means bigger average speed. Smaller gradient, less average speed. No gradient, flat line, no speed. You're standing still. Okay, so let's take a look at how we've got things. So let's say that we travel from point A, which is going to be down here. We're going to travel to point B, and then we're going to travel on to point C in that kind of way, and then to point D, and that'll maybe do us. Okay, so down here we've got point A, then we've got point B here, point C is here, and then point D is here somewhere. And I'll just smooth this out a bit like that. Okay, now I've got no numbers on this graph, so I don't know how far away A, B, C, or D are from each other, but I can immediately make some decisions about this. Okay, I know what's happening in certain parts of this graph. So let me grab a little red line. I know what's happening here. I can describe that. I know what's happening here, here, and here. I can describe those without using numbers. Here is the easiest. Okay, here we are at rest. Okay, or stationary, or stopped. We're stopped. How do I know that? Well, my distance travelled hasn't changed. Okay, the entire of this line is horizontal. So whatever my value for distance is here is the same regardless. So for all this time, my distance doesn't change. The only way that can be true is if I've stayed in the same place. So from B across to this little corner here, I'm not moving. I'm stopped. Okay, I know that at this point here, or between like where I was stopped and up to C, I know that I'm going at my fastest. This is my fastest speed here, because we've just said that the gradient is the average speed, and this is the steepest line. Okay, so this is where I've absolutely paid it. So if I've spent a bit of time at B, maybe running to a friend, started chatting, like I have friends, and then I've decided to absolutely peg it to try and make it to C in time to get to class or whatever it is. Right, so I run across to C, and then obviously, you know, being the supreme athlete that I am, I run out of steam a bit and I slow down here. So I know that this is slower, and that's not bad at all. Okay, so what's going on in the rest then? We can be a little bit more detailed. Okay, what we can say here is that this is traveling at a constant speed. Right. I know this because the gradient, again what we're talking about, the slope of this graph is nice and steady. It's consistently straight. Okay, that if I was traveling at a slightly weird speed, or I was speeding up or slowing down, I'd have lines that look like this, okay, where it's not at all smooth. But I've got just this line here that's going nice and steadily up. So this is a constant speed. And anytime you see a straight line, you've got a constant speed. That's constant speed. That's constant speed technically, but it's zero speed. So we don't say that, we just say it's rest. This again is going to be a constant speed. It's at its fastest, and this is a constant speed, which is slower than that. So that's not bad. That's not bad. I can visually see how I'm doing with this graph. Okay. Now, if we put some numbers in then, it becomes a little bit more interesting, because not only can I figure out what my constant speed is, I can figure out a few more things from that. So let's get rid of that, and let's put in an actual graph. So here's one I made earlier. It's like one of those children's art shows. And this is some form of distance graph. So we've got distance in meters up the side and time in seconds across the bottom. And let's say, for example, I want to find what's my average speed in the first 20 seconds. All right. So in the first 20 seconds, we can clearly see that we're traveling at a constant speed. Okay. How do we know that? Because the gradient of the graph is not zero; it is sloped upwards, but the gradient of the graph is nice and smooth, and it's a nice steady slope. So we've got constant speed here. Now what we want to do is we want to work out what that is. Now there's two ways we can work that out. We can do it by equation, or we can do it by graph. Okay, so the equation is average speed is equal to change in distance divided by time taken. Okay, to be completely clear with that. So we'll just call that S for speed equals the change in distance. Now the change in distance is going to be my final distance, take away my initial distance. So what's that? We need to go and pick some numbers off our graph here. So let's get our little dotty line out, and we'll go from here to here. So after 20 seconds, I have gone a distance of, there's 5, 6, 7, 8 meters. Okay, so my second distance is 8 meters. So that's 8. Take away my initial distance, which is kind of handy, it's down here at 0, which is 8 take away 0, so that's my change in distance, divided by the time it takes for that, which is 20 seconds. Okay, so I've got that distance and time situation going on here. So that's nice and simple. That's 8 over 20. So we don't take any heroics now. We can do that in our head, no problem. But we get our calculator out, okay, and we do, that's speed equals 8 over 20, which is 0.4. Now what's that measured in? Well, we've got distance in meters. Okay, so that's meters per time in seconds. So 0.4 meters per second is the average speed in that first section. Okay, next section here, we can pretty much tell that's at rest. And we know that's at rest because the distance doesn't change. It stays at 8 meters, doesn't go anywhere. And then this is the more interesting bit. What's going on here? So what we've got here is we've got a constant speed again. All right, this time faster than before. So we're expecting when we do our answer for it to be greater than 0.4. Alright, and again we're going to do it by equation just for the sake of it. So we have average speed is change in distance divided by time taken. Okay, so we've got to change our numbers up here. We'll just leave that in there, so we'll get rid of this. So my change in speed is going to be my my average speed is going to be my change in distance divided by my time taken. So my second distance is 25. My initial distance, since I'm only calculating what's happening in this section, I have to take away 8 from that. So we've got 25, take away 8. Divided by the time taken for that change, which is from 30 seconds across to 40 seconds, which is 10. Okay, so 25 minus 8 is 17, divided by 10. So my average speed is equal to 1.7. Exactly as we would expect, and again, meters per second. Okay, and that's cool. We can do it that way. Alternatively, what I can do is I can say that the speed, the average speed here, is the gradient of this bit of the graph. Okay, so all I need to do is find, for this section of graph, we've got a run across here, and we've got a rise across here. Okay? The rise here is 8 up to 25, so we've got a rise of 17. We have a run of 10. So the gradient is equal to the rise 17 divided by the run, which is 10. So my gradient is again equal to 1.7. Okay, so the gradient of a distance time graph gives you the average speed. Other questions you can be asked about this is like, how far has it gone after 35 seconds? And that's a really good question to ask a higher tier candidate, because you're all panicky going, right, I need to calculate gradients, I need to do weird things here, and in fact to find how far it's gone after 35 seconds, all you need to do is go across the 35 on the axis here, draw up the line, and then pop across and go, what's the distance? 16 meters. Done. No bother. Okay, well that's enough time on that. Let's move on to the actually difficult one, which is the acceleration problem. Okay, we have the equation that acceleration, which is for most intents and purposes is change in speed. There are a couple of instances later on when you do circular motion that's not just quite that. For right now, acceleration and change of speed are pretty much the same thing. So let's call acceleration is equal to your change of speed divided by the time taken. Okay, and if you're a big fan of letters, and that's because I like doing that, this is A equals V take away U divided by T. Okay, and the V and U have just kind of appeared. A is okay, A is for acceleration, T is for time, that's grand. Where did V take away U come from? Well, V is considered to be, is called your final, technically velocity, but for now we'll do speed, and U is your initial velocity, or initial speed. And you go, right, well, V for final speed, okay, you can call that velocity. What the heck is the crack with U? Like, why would you ever use U? Well, run your alphabet. What comes immediately before V? U. So V is the speed, and U is the speed before that. That's the idea here. All right? So basically, V take away U is the change of speed, what happened before and after, divided by T. All right? The unit for this is pretty much set, because what we have then is we have on our top line of our equation we have meters per second, and on the bottom line of our equation we have seconds. Okay, so we end up with the units looking like this: meters per second per second. And if you were going to write that as a unit, you would write that as meters per second, which is really, really, really awkward. Okay, but what that really means is meters divided by seconds divided by seconds again. Well, if you divide by something twice, if you multiply by seconds twice, it'd be meters times seconds squared, and the same thing's true for dividing. This becomes meters divided by seconds squared. So the unit for acceleration is the meter per second squared. All right, and again, sometimes it's a pretty straightforward question. You just got, a car starts at 10 meters a second, and then accelerates to 20 meters per second in a time of 5 seconds. Just pop the numbers in, job's a good one. But what if we want to have a slightly more extended discussion? What if we want to talk about, something that accelerates, then decelerates, then changes speed, then stays at steady speed over a period of time? Once again, graphs are the way forward here. This time we're going to have speed up the side in meters per second squared, and across the bottom we're going to have time. Again, we're going to measure that in seconds for the fun. Okay. Again, we're putting speed up the side and time across the bottom for the exact same reason as we did before, which is that we want the gradient of this graph to mean something. In this case, the gradient of this graph will be the rise, which is the change in y divided by the change in x. So it'll be the change of speed divided by the time taken, and that will be our acceleration. So on this graph here, the gradient is equal to the acceleration. Okay? And we draw a graph that looks similar in shape to the last one. Okay, but there, a little bit like that, something that looks like that. There we go. All right. Now, this becomes a little bit more interesting, because in this case here, what used to be constant speed here is now no longer constant speed. This is actually steady acceleration. Okay, notice I don't say constant acceleration, I say steady acceleration. Okay, that we're getting faster over a period of time because our speed's going up, time's going on, our speed is going up. Here, what was once now at rest on the previous graph, this is not at rest anymore. This is constant speed. Now, how am I getting that? If I draw a line across from here, what's happening at this point? This thing is traveling along in time with a speed that's not changing. And that speed is not zero, because zero is down here. So this is traveling at constant speed. Right? Over here we have steady acceleration again. But this time it's not as impressive as it was before. The speed's not going up as rapidly as it was before. Now the real temptation here is to say that this is steady acceleration but faster. And that's a really bad idea because you get a contradiction going on there. Like acceleration is by definition getting faster. Okay, so you can't have faster getting faster. Well, you can, but it's really awkward. So you don't say steady acceleration here, faster or slower. What you say is, in this case, this is steady acceleration at a lower rate. Okay, that it's not going up as rapidly as it was before. Okay, and if it was a steeper line, it would be steady acceleration at a higher rate. Now we know that this last line here again is a constant speed, and it's a higher constant speed than this one before. But the cool thing about acceleration graphs is that this can happen. That this graph can head downwards. I'm just going to shrink that and get out of the way for a minute. And what's happening here? Well, I start at a speed that's up there and I end up at a speed that's down here. So this object is actually slowing down. Okay? And there are a series of ways you can describe this. Okay? Decelerating, or deceleration, is the best way to describe it. You can call it slowing down, just about get away with that. You can also call it retardation, okay, which is kind of from the French en retard, to be late, okay, that you're slowing down. Okay, so deceleration, retardation, these are fine. Again, they are steady because we have a straight line here. So we've got steady deceleration, steady retardation, and that's it. Okay, that the acceleration is going downwards, and then you can have steady deceleration at a faster rate or slower rate if you're comparing two to each other. Right, so how does this work out in a real example? Once again, we go to the pre-prepared graph here, and let's have a calculate. Okay, so in the first one, what's the acceleration in this section? Well, the acceleration is 0 because it's traveling at a constant speed. We can prove that just by doing the calculation, that A is equal to V take away U divided by T. So A is equal to the final speed, which was 10, take away the initial speed, which is also 10 because it's finally here at 10, and then initially it was there at 10. And in that first section, the time taken is 5 seconds, which doesn't make any difference because it's A equals 0 divided by 5. It could be 0 divided by 50 million, that is equal to 0. So there is no acceleration in that first bit, meters per second squared. Okay, let's take a look at the second section though, because this is where it becomes interesting. Now, the gradient of the graph, we're going to do it the other way around this time. The gradient of the graph here is the acceleration. So we'll do it this way first, because we did it the other way first last time. It doesn't make any difference. So the rise of this graph goes from 10 up to what looks like 26, 27, 28. We'll draw a little line across just to make sure we don't want any trolls in the comments. There we go. So that's across to 28. So we've got 28 from 10, so we've got a rise of 18. And we've got a run from 5 across to 20, which is a run of 15. Okay, so the gradient of this graph is equal to the rise 18 divided by the run, which is 15. So the gradient equals, grab your calculator, do 18 divided by 15. You've probably got a scientific calculator, so you need to do the SD thing, and we get 1.2 for that one. What's the unit? Well, it's meters per second divided by seconds again, so that's meters per second squared. If that's not immediately obvious to you, I do recommend you go back and take a look at the rearranging equations and graphs live stream I did 2 weeks ago. It'll sort you out nicely with that. Okay, or we can use that A equals V take away U divided by T. That A is equal to the final speed, which was 28, take away the initial speed, which is 10, that's our rise, divided by our time, which is 15, and again we get A equals 1.2 meters per second squared. Okay, and that's all there is to that. Now the next cool bit though is this. What if I wanted to find the average speed here? Because the speed's changing. All right. Well, it's changing steadily. Okay, it's going from 10 up to 28. Right. So what we've basically got is we've got 10 goes to 28 smoothly. So the average is actually going to be the midpoint of 10 and 28. All right. So it's wherever the middle of this line happens to be. Okay, and the middle of that is going to be, just as with any two numbers, the addition of those two numbers divided by 2. If I wanted the average of like 12 and 14, I'd take 12, I'd add 14, I'd divide it by 2 afterwards, and I get 13 as an answer. The average of 10 and 28, my initial speed and my final speed, is equal to 10 plus 28, and then divided by 2. Okay, so I can find the average speed in any section that's smooth just by finding the midpoint, by add the starting number and the end number together and divide that by 2. Okay, so in this case that's 38 over 2, which is 19, which is bang between 10 and 28. Okay, so the average speed is 19 for that section. So that's kind of useful. You can get that straight from the graph as well. Now finally, the big thing to do. What if I want to find out how far this thing travels? In the distance time graph that wasn't an issue, because all you did was look at the kind of side here and go, right, well, how far has it gone? That doesn't exist in this graph, so I have to calculate it. So what I want to do is I want to use that distance is equal to average speed times time. Yep. So for this section, the distance is equal to the average speed, well, since it's not changing, it's 10, times the time it takes, which is 5. So the distance travelled is 50. All right. But wait a minute. What I'm doing here is I'm doing a speed multiplied by a time. And if I'm very, 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 very astute, what that is then is that is 0 up to 10 multiplied by the time. That in fact is this area here. Okay? And if I wanted to find how far it travelled in this bit here, because it's travelling at a constant speed, then I would take the 5 seconds that it was travelling that for and multiply that by 28. Okay? And that would be 5 multiplied by 28, which would be this area. I'll get a slightly better fill color because that was an ugly, ugly, ugly fill color. Let's try that one. No, I just can't select it. There we go. Ooh, well, that's okay. All right, things become a little bit more complicated in here because we have a kind of rectangular one. Now, if you're a super big fan of the trapezium rule, you can work away at that. I'm not a super big fan of the trapezium rule, so what I'm going to do is I'm going to say, well, if I want to find the area here, I want to find this rectangle, okay, which I will fill in a sensible color, like that. And I want to find the triangle sitting on top of this. And if this triangle tool fits the top of this, I will be utterly amazed. Yeah, that ain't going to happen anytime soon. I think we may have to use our imagination here. No, we're good. We're good. I love it when your software is better than you think it is. Okay, so if we can calculate the area of all these shapes, we will actually get the total distance travelled all the way throughout this. Just add them up. Okay, this shape here is 5 times 10, which is 50. This rectangle here, 15 across, 10 up, that's 150. This rectangle here is 5 across, 28 up, okay, which is 140. This triangle here is annoying because the area of a triangle is a half times the base times the height. Okay, so we're going to put the calculation in here. That's going to be 0.5 multiplied by the base of this triangle, goes from 5 across to 20, which is 15, times the height of this triangle goes from 10 up to 28, so it's got a height of 18. Okay, so the area of this triangle is 0.5 times 15 times 18, which gives me 135. So the total distance travelled is simply the sum of all those put together. So that's 135, 140, 150 and 50, giving me a total distance is equal to 475 meters. This only works when you've got speed up the side and time across the bottom. Watch out for this question. This is a really favourite of examiners. They love doing the find the distance travelled. And interestingly, if you write the following, if you write distance equals speed times time anywhere in the space where this comes up with, you get 0. Immediately you get, it doesn't matter what you do thereafter, you get 0. The first line you should write is that for a speed time graph, distance travelled is the area between the line and the x-axis. Once you get that, you can put them all together. And all you have to do is break it down into a series of rectangles and triangles and eventually figure them out. Watch out for the triangle sitting on top of the rectangle because the height isn't the full height. Okay? Happy? Alright folks, that's 9:31, so I'm 1 minute over. My apologies for keeping you a minute late. I would strongly suggest that in the comment section below there's a little worksheet for that with 2 sets of these, one distance time, one speed time graph, whilst it's fresh in your head. Have a little crack at that and see how you get on. I did get a request to do a couple of videos on answering these sheets that I put up. I'll certainly consider that and get on with it. I thank you so much for your attention. Please hit the like and subscribe buttons. It makes me get a bit of an ego, and it means that my wife doesn't give off at me so much because I can show her that people like what I'm doing. And all that remains to be said is, don't forget, physics rocks. It's true.